willing to share their 1.5 hours time with us, and let's see and learn from the subject. Thank you.
Okay, thank you, Professor Huang. And today it's my honor to introduce our company and what we do for us. My company is called DeepMentor, and we are doing the Edge AI deployment. Well, this is our company profile. Our company is established 3 years ago, and in Taipei. Why we established this company? Because we joined a program called TTA Prototyping Program Award, and we win this award. But if you want to win this award, and they have a condition. If you want to get a 1 million NT dollars award, you have to establish a company. So for the 1 million NT dollars, we established this company. That's how our company come from. And then in the 2020, we win lots of the AI competition and the award. We know the Professor Huang is in the IPS program. Professor Huang is the IPS is our accelerator. So from this we receive lots of help from Professor Huang. And now this year we have a certification from the Taiwan government. It means the Industrial Bureau of the Ministry Economics, 就是经济部工业局。Now our technology, AI chip technology and AI model optimization technology is approved by our government. Okay, now I will introduce what is the trend of the Edge AI computing. In 2018, Intel acquired Movidius. In this year, everybody talked about the multi-core DSP. So in this year, you will see lots of the AI company use DSP and the many core or multi-core DSPs and use floating point to deal with the AI problem. So this is the 2018. But soon, after 2 years later, China company called DeFi is acquired by Xilinx. And the DeFi's founder, one of his famous called Han Song. Yeah, he is now he's an MIT's professor. He published a very famous paper in called AI model compression. It's called the decompression. You can go to Google and search this paper. Its citation is very lots of. I think it's more than 4,000 citations now. Yeah, yes, very famous paper, and. These companies use the AI model compression technique to establish. And what is included in the AI model compression? One is called quantization, the other is pruning, and the third is use a Hoffman compression method to make the AI model become small. So it's very popular when you are using when you are deploying an AI model in 2018, you almost use the approach. And now, in 2020, it's very famous and a company called Exnor AI. The same, he also published an amazing paper. They use 1 bit to execute the AI inference. And in that year, everyone knows the low bit computation. It means in this year, we use 16-bit floating point. In this year, we use 8-bit integer. And in this year, we use 1 bit. But they will have a very serious side effect. The accuracy will drop dramatically. So many people did not like this approach. So in in the same year, we developed our accuracy log bit computation. So what we use is not use 1 bit, we use 4 bit to avoid this problem. So this is the AI computation trend. So in this year and the following year, you will see the log bit computation will dominate the AI deployment. Right. Okay. Before we talk about deep about the AI deployment, I want to establish some foundation of the embedded system, because each AI deployment is always deployed on the embedded system. So what is the embedded system? Embedded system is a single function. It means this system only do 1 or 2 jobs only, and it's tightly constrained. It means their resource like CPU or RAM or ROM is limited. It's not like a desktop. It cannot be expanded. And it needs a reaction, the real-time response. So this system will require you efficiency. And it's microcontroller based. It means you embed an ARM or MIPS processor inside your system. And then you will see he also embed a high-speed memory. Like you will have connectivity like 5G or 4G. And most important is a software hardware co-design system. It means in these systems, it needs hardware designer, software programmer work together to make this system workable. Now I will want to talk to you about the roofline model. When I talk about roofline model, it's not a new idea. It's about maybe almost 20 years ago. It was appeared on the paper. I hope everyone in this session you can look up the roofline model more detail. But in this session, I only give you a very brief introduction. What's a roofline model of an embedded system? Roofline model is for designer or software or hardware engineer to verify your system's performance. For example, the roofline model is vertical line is called P. The P means flux per second. The P means your computation ability. So if your CPU is more high speed, you will have high P. And we have a number called pi. The pi means the maximum computation ability you can provide in your system. And the other, we call it a RAM. In the RAM, we use a formula called beta. Beta means your memory bandwidth. The more memory bandwidth you have, the more beta you have. So if your memory bandwidth is unlimited, it means you will have a vertical lines beta. Your 90 degrees beta, it means you have infinite memory bandwidth. But in fact, you do not have this kind of bandwidth. Now, how we determine the system's performance is determined by the pi and the beta, because each time when you establish an embedded system, your CPU computation ability upper bound is designed by the number pi. And when you design, choose your memory type, like DDR2 or DDR3 or DDR4, and design your bus bandwidth, your beta value will be determined. So you have pi, you have beta, you can have an index called I. I means operational intensity is pi over beta. So this value is determined. So you have 3 values now. One is pi, one is beta, one is I. And then you can use pi and I to have this corner point, and you can draw this line. This is called roofline model. And in this roofline model, you will see they have 2 parts. One part is called memory bound. The other part is called compute bound. If your result is falling in this red area, it means if you want to improve your performance, you must make the memory bandwidth be more higher. But if your point calculator is falling in the green area, it means you must make your processor to be running more efficient or running more high frequency. So we use this formula to decide and check our system status and upgrade or modify our design. Well, this is the formula we just talked. Okay, we want to talk is this roof-line models, memory bound and the compute bound. If you want to handle the memory bound, it means you need to increase the degree of the beta. If you want to increase the degree of your beta, currently you have two approaches to use. First is use high memory bandwidth memory, like you can use DDR5 or DDR6, but it's very expensive. The other is increase your memory bandwidth. For example, one memory bandwidth is 64 bits. You can use 128 bits memory. Then you will have better beta value in these systems. And however, if your system are compute bound, what you can do is add more CPU core in your system, and then you can cross over compute bound. But I want to mention to everybody is, although using the roof-line model only separates memory bound and compute bound, but in real world, there's another bound in here. It's called power bound. Power bound, it means in your chip, you cannot have infinite power to use. But power bound is not appear on this graph. So in real world, we will consider power bound too. Okay, now we will go to our main topic, how we evaluate the AI model's complexity and how we use roof model and the AI model complexity together to evaluate our edge AI performance. First, AI model can separate into two parts. One part is called the computation complexity. We take the convolution layer as an example. Its complexity is n squared, k squared, and the c in and the c out together. What does the number mean? The m means the feature map length, and k means your kernel size. Everyone know this clearly. Yeah, I assume you have some AI models basic technology. And C is your input channel, C out is the output channel. In other words, your convolution layer handle many data. You will see these formulas is not linear. It's exponential. It's squared with your data input. So this is how we evaluate the convolution layer's complexity. And the other we want to mention is the data movement. In fact, in our real design, we think almost 90% or 95% is problem is limited by data movement. So we need to remember the data movement formula very clearly. And I want to think is about this. What they want to multiply for, because in current GPU systems, they use the 32-bit floating point to handle data. So the former part is the number, and this is each time you move the data's unit. If you use floating point, it's 4 bytes. But if you use 4 bytes, if you use integer, it is maybe become 1 byte or 2 bytes. But in our company, we use the 4-bit computation. So this part will become 0.5 byte. So in our system design, we also want to reduce the computation complexity and the data movement together. Then you will get a very good performance edge computing device. The other thing we not mention is the complexity also concerned with the neural network structure. For example, if you use the VGG16, you will see its structure is sequential. It means you data input and the blah 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 and the output, no branch, no shortcut. But if you use the MobileNet V2 structure, you will see they have a shortcut. The breakdown is the shortcut. when you have a shortcut, it means your data movement will be increased. But in data, so when you build up your own computation complexity formula and the data movement data movement formula, you have to take the structure of AI model into consideration. So in MovioNet V2, your data movement will be changed, not only this part. You will have to add the data movement into this formula too. That's the AI model's complexity. Okay, after you put this together, we give you an example how to analysis. This is the BGG16 we see previously, and we just get this column. I put in more bigger here. You will see is flux. It means you do this kind of flux is almost 115 teraops, and you will have see your memory access will have these two values. The first value is how you do your convolution. When each time when you do convolution, you will get your kernel weights and your input value together. Sorry. And this part is how you write your feature map into the memory. So you have these two memory operators together. And how we get the value I? Remember, we say the value I is your computation over your memory complexity. So this part is your computation, and this part is your memory bandwidth requirement. Why we multiply 4? Because we use 30 bits. So after this formula, we have 25 flux per byte. Remember this value. We will use it later. And then the same, we do the same analysis on the MovioNet. After the formula, you will see is 7 flux bytes. And this is our reference data. Okay. Now we put all the things together. If you have an NVIDIA GTX card, in this card, your pi means your peak performance is 11 teraops, and your memory bandwidth is almost 500 gigaops. So you will have your pi and your beta. So use the roofline model formula, you will have 24 pi. So in this when you get a GPU card, you can use the pi, beta, and IMAX to draw the roofline model. So every time when you get a new hardware device, you can draw this roofline model by yourself. It's very important. Then we use the value we just compute previously. In previous PowerPoint slide, we know the MovioNet only have MovioNet have 7. Is I value is 7. It means your operational intensity is 7. So you will in this graph you will use the 7 in your horizontal line, and you will see your teraops, effective teraops 3.3. 3.3, but you have 11. It means when you run in MovioNet on GTX card, the GTX computation is waste. But you utilize all the memory bandwidth on the GTX. However, if you use the BGG, in BGG16, you will see is IMAX is 25, and you will see, okay, is 25, and the IMAX is 24. So you will see it full utilize the GTX computation power, but it did not full. It also utilizes all the memory bandwidth. So if you are both, you will think, okay, BGG16 is better. It full utilize the GTX computing power. So we hope every design, your algorithm can full utilize your hardware. It's a good algorithm for the device. So in our edge device deployment, we will always and discuss with our customers what kind of algorithm design you want. And once the algorithm is designed, is determined, we will choose a better hardware configuration to make their roof-line model like BGG. The best point is at this corner. If your design is like formulate in this area or far from this corner, it's not good design. So this is a very good tool to, I think it can help everybody to tuning their AI architecture and the AI model. For more detail, I think you can reference this PowerPoint slide. You will talk about how to use roof-line model to doing architectural performance tuning.
What happened is in the cloud?
The same.
Yeah, right?
The
Because
same.
we need to use every cloud, right?
Yeah. Okay, now we will share some experience about we deploy the AI model on ARM CPUs. These 4 processors we used before. We use a Raspberry Pi, we use a ROC chips, 2 ROC chips, the CPU, and we also use the MediaTek chips to test our AI models on the ARM processor. And in this graph, I want to introduce one concept. One is called intercore, one is called the intra-core, one, the other is called intercore. When we're doing this multi-core deployment, we choose different runtime environment. One is called the TF Lite, is provided by Google. The other ARM compute library is provided by ARM, and the third one is NCM, and is provided by Transcend, Tenshu. Okay. Now we use 3 different library, and we get the same trend. In these 3 library, do you want to guess which is the best one? It's NCM is the best one. Yeah, so you must be very careful and very respect the R&D and the programmer in mainland China. They are doing lots of work on the AI deployment too. Okay, now back to our topic. We want to introduce the intra-core and the intercore. What is intra-core? When you're doing the multi-core processor, you will see they are group processor in different cluster. We take the MediaTek X20, for example. They have 3 clusters. One cluster is A72, and the other 2 is A53. Within the cluster's communication, we call it intra-core communication. The intra-cores means they share the same layer 2 cache. Inter-core, it means they do not share the same level 2 cache. Now, why cache is so important? Because when you want to synchronization data between different clusters, it means if you want to synchronize data in the inter-cores, the cache coherence protocol will drop your performance dramatically. It means you will waste lots of time to synchronize this cache data, and your performance will be dropped down. So when you want to deployment your AI model on the ARM CPUs, we take BGG for example. You have to partition this BGG model into, for example, they have 3 clusters. You separate it into 3 parts. But the 3 parts is not equal. For example, you think the cluster 1 is more powerful, so you must let your cluster 1 do more job. And cluster 2 and cluster 3 is not so powerful. So in this case, cluster 3 do less job. How to optimize this system? You must let the cluster 1, 2, 3 have the same execution time. When you make the cluster 1, 2, 3 have execution time, from the formula from mathematical formula, you can prove they have the maximum performance. And we have published a paper in 2020 and AICAS talk about these things. If you are interested, you can look at the paper, and the more details formula we also describe in this paper. That's why we do in the unprocessor CPU. And the other is, guess what? This 4 processor, which is the best one? In fact, MediaTek is the best one. And in the best one case, we turn off these two A33 cluster. We only use the A72 cluster, because when we turn on these 4 cluster, we always find the cache coherence make our performance drop. So in multi-core systems, you will be very carefully design your cache coherence design. It's the performance bottleneck. And the other, we also deployment the AI models on the ARM GPU. We choose the same platform too. The Raspberry Pi did not have the GPU programming API. We use OpenCL to run our deployment our AI models on this processor. But because OpenCL cannot execute on Raspberry Pi, so the experience on the Raspberry Pi is not available. So we use in these 3 platforms. The same, we use the VGG as our test bench. And you will see we choose the ARM's architecture is Mali generation 2, or this is generation 2, yeah. This is generation 3. Do not use the Mali architecture generation 1, because you cannot execute OpenCL on the generation 1 Mali. Now, why you cannot use the OpenCL on the generation 1 Mali GPU? Because its architecture is not programmable. It's always fixed. But in generation 2 or generation 3, you will think you have a shader code. It means you can run a program on their GPU. So we do the same experience on the Mali's GPU. And then we get a very amazing result. GPU's performance is worse, very worse than you run it on the CPU. It means I run the model on the CPU is better than on the GPU. We found this problem and we asked why. It means GPU have more computing power, but why GPU is more slowly? The problem is context switch. What is context switch? We take BGG for example. You will see there are much of layers, and each layer have their own private parameters. So when you want to compute one, layer 1 become layer 2, you need to do a context switch to change the parameter. However, the OpenCL on the ARM's GPU, context switch is very slow. It's about use more than 30 microseconds to complete one context switch. It's too slow. So the more layer you have, the more context switch overhead you have. So yeah, so that's why ARM do not encourage you to use the GPU as an AI accelerator. That's the reason. Now we will ask their ARM's many programmer and ask them, is it possible to increase or reduce the context switch overhead? The answer is no, because the architecture does not allow them to do this. In fact, in this architecture, there are many registers. There are more than 1,000 registers in one-time context switch. So that's why the context switch needs so many times. Okay, now we get into the more popular platform, NVIDIA's JSON platform. Okay, the JSON platform from the computing power from the lower to higher is from Nero TX1, TX2, and Zabbia NX and AGX Zabbia. Okay, we take the Zabbia for example. These two Zabbia usually, in fact, is not designed for embedded systems. It's designed for autopilot. But we think NVIDIA is do some function cutting and making into a small SoC platform. We can take the Zabbia for example. the high-end Zabbia, you will see they have 8 CPU, and they have many CUDA's core, they have tensor core, and they have NVDLA. You will see the Zabbia SDK told you have a 32 teraops in integer 8. It means you use these 3 kinds of heterogeneous computation, you can get this kind of performance. But if you want to use the floating point, you will see your performance will be dropped. So in future, you will see the integer 8 operator will be adopted by many systems. It's the future's mainstream. And NVIDIA also do this. And the Zabbia NX is a simple version of AGX Zabbia. Why they simple is because for the price, for the marketing segment, marketing need a more cheap device. So they make the Zabbia NX. But in fact, if you want to buy the Zabbia NX or Zabbia now, you will wait for at least 20 weeks. It's because now is semiconductor show of stock. And in school, I think many labs have a TX2 or TX1 or Nano. We take the TX2 for example. In TX2, you will think they have 6 CPU and the CUDA core. But in TX2, you will see your teraops is not very high. It means you only have a 1.5 teraops. So in TX2, the roofline model is very important for you. You have to use the roofline model. You can use TF2 to draw TF2's roofline model, and then check your aberration in this roofline model, and you can decide which kind of aberration you can use. That's what we do on the embedded system. And also, you will see, I think many people have TS1, but they do not aware they have. Because TS1 is used in the Nintendo Switch, 任天堂 Switch. Inside this console is used TS1. And then just the Nano is very cheap and very available developer kit in the market. But you will see the just the Nano only can execute floating point, 32 floating point. So if you use the JSON Nano as your project development kit, you will be very careful because the performance will be very worse in real case. Okay, but in our HAI deployment, our customers always choose Zabbia for their first priority, because its computation is very high, and you will see it's a future trend. In the future, you will see the heterogeneous computation is everywhere. In Zabbias, we will use the CPU, the GPU, and the DLA to doing AI-related job. But we will use PVA and ISP to doing the image processing. For example, what is PVA doing? Do you know the OpenCV, a very famous compute library? You will see PVA is a hardware-based OpenCV accelerator. So you want to doing some traditional compute vision library, you can use OpenPVA to accelerate it. ISP is used to tune your camera's image quality. If you want HDR or something special effect on your camera, you can use the ISP. And this MN accelerator is used to stereo and optical flow. Do you know why NVIDIA put this? Because they want the Zabbia also become a game console too, so they put this. If you do not want to do a game console, I think you never execute this function. Okay, now when you use the NVIDIA's platform to deploy your AI model, you need to expect their GPU's architecture. For example, in NVIDIA's Zabbia, they use the Voltas GPU. Keep in mind, every generation's NVIDIA's GPU have different performance. And the performance is determined by their cache, hit rate, and the coherence. So if you use the Volta GPU, the first thing is you must expect their cache size and the cache coherence latency, and use this value to draw your roofline model to evaluate your system's performance. It's not an easy job to do this because many value NVIDIA did not tell you. You must write a simple program to do the test bench to get these values become available. The other is when you use NVIDIA's SoC, you will see the DLA, is Deep Learning Accelerator. NVIDIA's open this DLA become public. So you can public domain, you can get the NVDLA's source code. I mean the source code, it means the very low source code. It means you can get this and tap out your own chip. But NVIDIA only provide the 16 floating point accelerator. The integer 8 for design circuit, they did not release. So if you want to do the some Taiwan's academic, like I think the E3, Gong Yue, they have based on this design, add the integer 8 operator on it. I think like Zhongshan University's the team also do the same things too. Now when you use the NVDA, you will meet one major problem is because NVDA is not like CPU, it's not like GPU. They have their own compiler to do the model convert. So some model cannot be successfully converted by deployed on NVDA. So in our real case deployment, the compatibility number one is CPU and the GPU, but the compatibility for NVDA is not good enough. So we, in real case, will avoid to use the DLA because the tools is not mature enough. Okay, we can put it together to see this NVIDIA's provides function. Why we talk about NVIDIA? Because we think NVIDIA's always do something ahead of us, and we can learn something from them. NVIDIA always make the throughput become teraops. It means in the future, if your design AI chip cannot provide teraops computation, the fuel market you will have. And I think NVIDIA make this entry barrier become more higher and higher, but it is true. And the other is you will see NVIDIA always focus on doing computer vision. Why do not handle the voice? NVIDIA seldom say they can handle voice or natural language because the natural language and voice is not belong to edge. They always in the server. So NVIDIA in the edge device seldom provide this kind of benchmark. Okay, this is our final slide. We will talk about the edge AI's market. In edge AI, we use the AI model's parameters number to separate the market into 3 segments. One is below 7 million parameter. We call it tiny ML. This ML, you can use the MCU and the AI plus an AI IP to accelerate it. But this model only can use in very simple environment. For example, if you put it in the outside, it's not suitable because a tiny ML cannot overcome the complex environment change. And the other is cloud ML. It's more than 100 million, 1亿个参数以上. We call the cloud ML. And the cloud ML will convert will be shrink down to become HML. For example, if you want to do the object detection, for example, if you use a BGG, in the 4 or 5 years ago, VGG only can execute on the cloud, but now you can put a VGG on edge devices too. So in fact, in the real world, you will see the mainstream of AI deployment is from 7 million to 100 million. This is we call in HML. This is a very good market for Taiwan because when you want to implement this, you need AI ASIC or Edge AI FPGA, especially the AI ASIC. So I think a Taiwan company can put more attention on this segment. For this segment, I would say not touch it because this segment almost dominate my ST micro, almost. And this is what we can do. And the cloud systems do not touch it because it's always dominated by NVIDIA. NVIDIA never allow everybody to touch this segment. So this is our future outlook for the AI smart doors. Okay, thank you. And these are my presentation today. Thank you.
Any question? I have a question though. Right now, there's a lot of AI chips, right?
Yeah.
What do you think about? Because you talk about NVIDIA needs more like more computation capability than this chip that narrow. They are doing that, right? So there's like hundreds AI chip vendors.
Yeah.
But any comments on AI chips?
AI chips, I think this market needs lots of AI chips. So in narrowing, they focus on about this segment, about 7 million to 10 million segment. So I think each AI chip can take one part of this market segment. Now, because AI chip have limited memory capacities, we use the different memory capacities to do market segment. For example, we cooperate with Israel's AI chip company called Helio. Their segment is this one, almost 10 millions. So I think different AI chip, according their internal memory size, they will have different marketing segment naturally.
Okay. So in your case, you can do all spectrum.
Yeah.
Like before clock.
Yes.
Right.
Yeah.
So all the AI chip can actually collaborate with you.
Yeah.
So what's the benefit of having collaborate with you? Or they can have their own platform, right?
They can have their own platform. In fact, what we do is make them have a better AI parameters. By our technology, we can make them have 8-bit or 4-bit parameters more accuracy than other companies' technique.
Okay. So kind of speed their computation.
Yeah.
Your movement is less.
Yes.
But that's kind of important, right?
Yeah, very important.
Right. So any reason they are not working with you, right? Because of still, I think that would be like super demanding.
Yeah.
Because you are so obvious, right? 8 bits and 4 bits, regular is at 32 bits. So any hesitation for them to work with you?
So far is no.
No.
Yeah. Because we do not do our own chip, so they are safe.
Yeah. 那老师这边。
Director, Mr. Chair, excellent director. Yeah, actually, well, we're doing some solutions for design automation. So, my question is that basically the company is doing the platform evaluation, right, for the computing power.
Yeah.
Is that right?
Yeah.
Okay. So actually, my question is just like as follows. So, what do you think that what kind of a solution that you need for the future AI chips would be better fit for this company?
In the future, for a CNN, convolution neural network, I think the problem is almost solved already. And next future in our company, we invest on the transformer. How to make transformer become hardware? And because transformer is the new AI model and the new AI algorithm. I think this next challenge is here, not in the convolution neural network anymore.
So you mean the transformer means the transforming the different neural network to your target, right?
Not yes. The transformer it means a new AI model. It is not use the convolution as their operators not anymore. So the operator is not convolution. It's a new operator. So you have to redesign your AI chip to apply for this kind of new AI algorithm.
So as you mentioned, you're targeting the next transformer.
Yeah.
So basically, you already have the technique available for the precisely the attention over inside the transformer.
In fact, the detail I did not know very well because we cooperate with the NTHU's lab, and they help us to do this research. And we only adopt and take their research result become product. So I'm sorry I cannot provide you any answer.
I think I heard you talk about that. So any others questions? Yeah. And then how about applications then? I mean, it sounds like the application is kind of very wide, right?
Yeah.
So any specific application? I think AI already have their own position.
Yeah.
Right? But then what is more killer in your application? I mean, what is more killer application?
Smart retail and surveillance.
Okay.
Okay, smart retail is very obvious. Means we put the AI on the advertisement machine, and they can do some people counting and hot area analysis, and so they use this data to evaluate to evaluation the advertisement result is good or bad.
But let me question on that then. I mean, because that already exists, right? So
Yeah.
are you going to replace them, or the reason for replacement because?
Not replacement. The machine is the same, but we add extra AI device on the old machine.
I see. Okay. So, yeah. Okay. Any question there, back there?
I have a question. Since you talked about the memory and the computing in the roofline model, so recently some companies are also doing the in-memory compute.
Yeah.
So I want to know where does that lie in that model in terms of performance and also in these segments?
In memory compute, you cannot apply roofline model. You need to build the other model because in roofline model, okay.
Yes, this is like more
Yeah.
segregated in terms of compute and memory.
Yes, in roofline model, it is basic assume your machine is non-human-like machine. If your machine is not non-human-like machine, like in-memory compute or quantized compute, this model cannot be applied.
So for smart memory, that will not lie in these segments. Because I read in some articles that recently some companies are also doing the in-memory compute for commercial users also. Recently, like TSMC launched something few months back.
Yeah.
So that's why I was wondering that in which segment that will go.
I think your in-memory compute can be separated into two subtopics. One is real in-memory compute. It means your compute unit is beside your memory cell. The other is called near memory compute.
Yes, inside
If your compute unit is near memory compute, it still follow the non-linear architecture. So you can use this. But in memory compute, you cannot use this roofline model.
How about the applications? Any questions? I think you guys have some preparation for questions, right? So can you Sean?
Victor has a question. How can you relate the AI tech to 5G? Which cases are they compatible to use in 5G application?
How can you
How can you relate the AI tech to 5G use cases, are they compatible to use in 5G application?
Relate back to 5G.
Of 5G, okay. In our own experiments, in fact, in 5G you have a lot of download bandwidth, but still you have limited upload bandwidth increment. In the edge AI's deployment, we want to solve the problem is the upload problem. It means we do not want to user to upload the raw data in the cloud. So within the first mile for the edge AI is the first mile for 5Gs. Maybe I can share an example for you. In fact, in the天母 baseball field, the 天母棒球场, yes, we have to do some 5G and AI together. We use a 20 high-speed camera to capture the baseball players when they hit or and they throw a ball, and we use the AI. We use the 5G to the 5G data did not send to a cloud directory. In fact, they send to their fork, and then we use AI in the fork to build the model of each pitch or each hit, and then make the model immediately to review by the player. So they will, in about 3 or 4 minutes, they will know their performance is good or bad. That's why what we do now, combine 5G and AI together.
Okay, so you can have a 2-minute response, the computation and the feedback to the player.
Yes.
To see how they do the next pitch.
Yeah. Yes. Now they take advantage of the 5G's high bandwidth transmission.
Is that having integrated assistant so the coach will see that, or they just have fun for now?
Yes, it's integrated, become a system, but this project is not developed by our own. We cooperate with the Thai TIDA together to build this project.
We collaborate with them.
Are there any model to evaluate the device, expand the roof-line model? And also, as you mentioned, that the memory bound, compute bound, and also the power are critical. Is there any other parameters that always focus on?
This is a good question. Is something better than roof-line model? Yes. You will see lots of papers to enhance the roof-line models. So I think I can suggest you to do some research about the enhancement of the roof-line. Lots of paper. So many people want to enhance this and add more parameter on it. It's true. But today I give you an introduction, very simple introduction that can make everybody very interested about a roof-line model. Yeah, I think it's a good basic tool, but they have lots of extension too. Yeah, and your answer, you can do some paper survey. I think you will get your answer very quickly.
Yeah, I think that's very good introduction because we are doing edge computing and we need to worry about the design and also yeah.
I have one more question. Since for that question for 5G use cases, you talked about the bandwidth and spectrum for AI. So I wanted to know that currently are there any real-time use case solutions or in near future for latency stringent requirements for 5G in the low latency use case?
Yes, there's a very important use case in the medical, in the surgery. They're almost like real time, very real time. Remote surgery is a very hot topic, but very difficult for school to do experiments, because you must invest lots of equipment in this. This is need most real-time application, and so far only 5G or 6G or fiber can achieve this job.
Would that do more assisted based or like it's not automatic surgery, right? It's
Yeah.
assisted based. Is that I don't know because there's certainly some tech, like time, right? So the
Yes.
time is very critical. So
Yeah.
so it's still possible for remote surgery thing involving.
Yes. This question we have discussed with the, the IDA. Yeah, IDA means South. Yeah, South Taiwan have a IDA 医院, IDA hospital, and we can talk with them about the problem. And they so far they think the Darwin sees, yeah, this machine maybe can detect, can use 5G to do the remote operators.
Actually, I had an interview with Liu, right? He was here my podcast. He mentioned that he did all like 3,800 surgery for Da Vinci.
Yeah.
Da Vinci surgery, right? And turned out they tried to automate it, but then after discussion, they said no, forget about it because of the so dynamic in terms of the situation, and then so at the instance they have to make a decision, right?
Yeah.
So right now he more like assist.
Yeah.
To
Yes.
tell you what is organ there instead of like tell you what to do.
Yes.
So it's just make sure you don't make mistake. Like there's a big percentage you make mistake. So maybe we can actually send you the link. You hear what he said. But that's the suggestion is that because of limited talents.
Yeah.
Maybe something can be improved further, right? But that's a good. My one last question for me, and maybe there's a question from the audience. How about the security part? Do you worry about it at all, and then you don't, or someone is taking care of that?
Security.
Right? Like, there's a lot of computation.
In fact, next problem we will face is a security problem. That's true, and because we sponsor the NTHU's PhD student, and one of the students is help us to do the security part enhancement and the research. So we care about these things, but we think they will only happen about 3 or 4 years ago.
Okay, so do you know John Zhao?
No. Yeah.
Actually, maybe I can introduce you to him and to chat if there's a collaboration.
Yeah.
Security and also because they are doing security for edge computing.
Yeah.
I think Stephen is kind of helping in that space. Okay, any more question here? Con?
Yeah, hello. What hardware will you suggest for use case in which the real-time data is coming from wireless sensor network? Like we have wireless sensor nodes and the data coming, the time series data in GBs almost.
You mean what kind of hardware platform?
Yeah. Can we use the Banana Pi for that?
I think it is in school. I always recommend people to use the NVIDIA's platform because the resource and the computation is more high, and the resource is abundant resource you can look up. If you choose this Raspberry Pi,
because it's low power.
Yeah, it's low power, but if you want to, we use the Raspberry Pi, we cooperate with the Google's HTPU. Do you know this? You can use the Raspberry Pi and the Google HTPU together to make your project go smoothly. Because the Raspberry Pi's computation power is too slow. But if you use through the USB connection to the Google HTPU, you will get a 4 teraops operators, the computation power. So in your case, if you want to use a Raspberry Pi, I suggest you to put the Core HTPU together inside your system.
Yeah, and it will be running on the edge.
Yes.
On edge.
Yes, real edge. You can Google and the Raspberry Pi plus Google HTPU. You will see lots of article and discuss about this kind of combination.
Okay.
With that combination, the cost comparison between that combination and the NVIDIA
Okay, if you use Google HTPU, Google HTPU can replace the TS2.
Oh.
But they cannot compete with the Zabbia. Zabbia is still very strong. Yeah.
Okay, that's good. Good to know that. Thank you. Any more questions here? Now, can I thank Dr. Zhou and from the DeepMentor. I think he's a very bright future. I think if you're interested, you can work for him. Will become a millionaire